Hi everyone. Today we're going to introduce a whole bunch of new terminology and definitions that we'll use to characterize a lot of the properties of Markov chains. The first of those quantities is somewhat significant. It's going to show up over and over again. It goes by a lot of different names. For us, it's a sort of a long name. It's called, I'll just tell you the name first, then we'll talk about what it is. It's called the state occupation distribution. And it's a vector, so you might find it named something with the word vector in it. More important than the name is what the quantity really is. And so it's primarily about the idea of this quantity we want to introduce is a vector, and each of the elements of the vector is going to be the probability that the system that you're interested in, the particular system being modeled by a Markov chain, will be in a particular state. So like the probability of being in state 1 will be the first element, and the probability of being in state 2 will be the second, and so on. So this is not talking about transitions, and each of these probabilities is evaluated at a particular time. So let's just, without further ado, introduce this quantity. So it's a vector, and we're going to call it lowercase u. An arrow over the top of something is how I indicate a vector. So we'll write it like this. And it's going to be a row vector. If you're, that might be an unconventional definition for you for a vector. But anyways, let's write it out. So it's going to have a bunch of different elements, or u1 at time t. So that's the first component. u2 time t, and so on. And I'll just close. I won't name the size of the thing. But each of these components of the vector is the following. So uj at time t is the probability that the system at time t is in state j. Right, so you can see why this might be. I think you might see then why this is an interesting vector to talk about. You provide a time, and then you have this nice array of probabilities of being in each of the different states. So it's handy for all kinds of things. I want to emphasize again that this is a row vector, and that, of course, it's a convention choice. It appears to be the most common convention choice for this thing. So I'm not going to alter that. But you might get into a little bit of trouble if you forget this, because particularly in statistics modules, as far as I can tell, it's pretty unconventional to introduce a vector as being a row vector. And so you kind of get in the habit of thinking of it as a column. Of course, that doesn't matter if all you do, so let me just make this brief aside over here. If all you do with two different vectors, say, are things like this, A dotted with B, like a dot product or something. It doesn't really matter when you write them this way, whether or not you think of it as a row vector or a column vector. The dot product, this is sort of a geometric statement about these objects, and you don't have to say much about whether or not they're rows or columns, or at least you can be careless about it, or you can hide it or something. But you will get into trouble if you did something like this. So let's say you wrote a vector here times a matrix. Now if that vector had n components and that matrix was n by n, this product would only work if the vector was a row vector. It wouldn't work if it was a column vector. Instead, if you wanted a column vector, if it were a column vector, this product would work. But it would not work as a row vector. And so, or is that true? Let's see, the row vector might work in that case. But anyways, you see what I mean? It makes a difference if you're going to start writing matrix multiplication things. whether or not your thing's a row vector or a column vector. I'm sure that's all familiar to you. I just wanted to remind you that we're using this thing as a row vector. Okay, now we're going to introduce a proposition about it, and we'll prove it. And the proposition has a couple of different parts, but they are a little bit clearly kind of follow from each other, I think. Okay, so the first part is to say that the state occupation distribution at time n, I have to be careful with my u's and n's here. You can see they pretty much look the same. Is equal. You can write it as the occupation distribution at time n minus 1 times the one-step transition probability matrix. I'm going to put that over this side here. Just so it's clear what that is. Right, and so we're immediately writing matrix multiplication with this thing. So this is the first part of this proposition. So basically what it's saying is if you have the state occupation distribution at time n minus 1, if you multiply it by the one-step transition probability matrix, you get the vector at the next time, right? So it's sort of like an incrementing machine. You know, you hit this thing with the matrix and it increments the time. Okay, and the next claim in the proposition is relatively straightforward. It's to say that this vector at time n is equal to the vector at time 0 multiplied by the one-step transition probability matrix n different times, right? So I think it should be clear that this thing follows, that number 2 follows from number 1. But okay, so let's do our proof. All right, so we're first going to work on number 1. We'll say, we'll write out the left-hand side, uj at time n. That subscript is, I'm going to rewrite that. Uj at time n, right? So we'll just write it out as a probability. And then what we're going to do is use the total probability theorem. Like that. So that's the definition of these guys, of the component j of this vector. Okay, and then we'll use the total probability theorem. We'll say this is a sum over k of the probability that xn is equal to j, given that xn minus 1 is equal to k. And you can do that if you then multiply by the probability that xn minus 1 is equal to k. And then you sum over all the k's. I guess I'll just put infinity here so we don't have to say how big the state space is. I think I probably should have modified this as well over here where I say, you know, j is in the state space. I guess that's probably relatively obvious, but we should have probably said that right from the start. Okay, and so we'll continue on with this proof. I think maybe you can kind of see sort of what's going to happen. Do you recognize this quantity right here? Right, that's the probability to go from state k at time n minus 1 into state j at time n. So one step from k to j. And so that's an element of the transition, the one-step transition probability matrix. So we have a sum over k, and I won't bother with the boundaries at this point since we've already said what they are. And so this is p from k to j times this probability, which is, sorry, I shouldn't have even written that. What is that probability over here? So do you recognize this guy? Right, that's the state occupation distribution. That's its kth component at time n minus 1. And so we have uk at time n minus 1. Right? And if you stare at this long enough, you should be able to recognize that this is the multiplication between a matrix and a vector. And so this is equal to the vector u times the one-step transition probability matrix. Okay. 2 does follow from 1. Actually, I think I'm just going to leave it to you. Maybe you'll enjoy it working on it by yourself. You can ask me if you have troubles with it. The proof might be in the sheets. Now we're going to start introducing a whole bunch of different kind of names for types of states. And this is the type of portion of a lecture where you probably won't absorb it all right away. You're going to have to turn back to this part of your notes to remind yourself about what these various definitions are, because they kind of come a little bit too many at once. So what we're going to talk about is classifying states. And the idea is illustrated, or like the need for this is pretty well illustrated by one of the previous examples we saw. So let's look at the gambler's ruin. So remember or recall, let's just sketch its directed graph representation. I guess I should just, there. And you remember how this thing, well, maybe you don't, but it looked kind of like this. So on the endpoints, there were these kinds of transitions, like this. So that if you got to the ends, you were stuck. And then there was like, you had probabilities for going like this. I guess that's, I'll leave that one. And you could also sort of march down the states like this, right? And so it should be clear that like this state here is different in character than this state here. But this state here and this state here are similar in character. But these kinds are kind of the same, but they're a little bit different. I don't know. So oops, there's something wrong with what I've done here, right? You can't if there's a probability of 1 for returning straight back to it, you can't have that. So that doesn't belong. And similarly on this other side, whatever it is that comes right before, so let's just put it in. Right. From there, you can get into this last state, but you cannot come back out. And so there's an arrow like this, but there's not one coming back out. So these two are similar, but not quite the same. One of them you can get into, or both of them you can get into. Maybe they are the same. Well, let's see. So anyways, the whole idea of this section is to start giving names to these things so that we can kind of have a better vocabulary for them. All right, so the first thing I'm going to do is name these ending type states, right? So this is called, so a whole bunch of definitions here. So we'll say that if PII, which is the probability to go from a state right back to itself, if that's equal to 1, which is the case for both of those two ending ones, then we say that I, we call it an absorbing state. Right? So that's the term we're going to use for that. In other words, there's no way out. Okay. So that's one. You can think about whether or not there were any absorbing states in the four heads example, the four heads in a row example. You should try to look for those. Okay, let's go on to our next one. We're now going to say if Pij is 0, for all I, but a fixed j. All right, so let's think what that means. It means the probability of going from I to j is 0 for all I. It means there's no way to get into state j. All right. So it's a pretty weird situation if you think about it. I don't know, but maybe it comes up. So we're going to say then j is called an ephemeral state. Okay, so there's no way in. Right. Well, actually, there's sort of one way in, right? You can start in that state. It's a bit of a weird singular situation there, but you can certainly imagine some system in which you start in a state and then you never, or let's see, how do I say? What does this mean? You can't come into it. Yeah, so you start in this, it's not so weird. You start in this state, you leave it, and then there's no way back. That doesn't seem so unusual. So yeah, you can, there's no way in, but you can start there. Okay. So let's look at a couple of examples. Right, so let's say we have this guy here, and there's a probability of a half of going here and a half of going there. And then there's some, interesting business for going back and forth between these two guys, but no arrows pointing back to it, right? So if you've got that, then this guy here is an ephemeral state, right? You can start there and then you launch. There's a you don't know which way you might go. You leave somehow, and you're never going to come back. It could also be a simpler version, like where you have a state like this, and then there's some pair of states, again, like this, and you can go like that, and then maybe there's ways to go between these two guys, but there's no way to return back to the one that you started from. And so for this one, this guy's the ephemeral state. So ephemeral states aren't that bizarre, but they are kind of interesting. Okay, the next thing we're going to introduce is a little bit more complicated. So it's not just introducing a particular state. We're going to introduce something called the first passage probability. So we'll say, so this is the first passage probability, right? And the label for it looks like this. We'll call it Fij. Oops. Fij. And it has a time n, right? And this thing looks like this. So we'll say this is the probability of having the following sequence. So x1 is not equal to j. x2 is not equal to j. So at times 1 or 2, you're not in state j, and so on. But at time n, you are in state j. So all these things over here refer to state j. And at time 0, you started at state I. Right? So the idea here is, and so for this, so for n greater than or equal to 1, right? So this is the, let's put it in words. This is the probability of first reaching state J after n time steps after being in state I. Right? So it means you start off in state I, and then you wander around, and then eventually you hit state J. That's the sequence we're interested in, and we're talking about the probability that that happens in n steps, right? So you don't reach step J until n time steps after the starting one. Okay, and then there's sort of a so that's the first passage probability. There's sort of a special version of that. The first return, I guess I should make this a separate definition. The first return probability all right, and this guy, he only has one index, so F I and a time argument, and this guy is defined to be the first return probability. Sorry. Oh dear. That's it. We don't need any of this. It's all in terms of what you saw above, right? So the first return probability is just this, and it's saying that you start off in state I, you go out and you wander around, you have a sequence of states that you go through that don't include state I, and then after n time steps, when you get to the nth element of that sequence, you find yourself back in state I again, right? So that's the first return probability. Okay, and now we're going to introduce a related quantity. I don't have a name for it. We're going to name, or we're just going to give what it is. So we're going to say Fij. So summing gives the following. Summing, I should say, over, well, you'll see in a second, so there's no reason to write it out. The following. So we'll say Fij with no time index. So removing that n implies the following has happened: a sum over n equals 1 to infinity, or I guess you can start off at time step 0. Is that what we were doing above? So let's do that. Although I think this is actually defined with a 1 there, but it shouldn't matter. You can call your time step whatever you want. This is the sum over Fij at time n. Now let's think about what this means. So I'm going to sort of sketch out what the sum is. So let's write the very first one, right? So that's the probability of going from I to j in one step. Right, so that's the first term. The second term is the probability of going from I to j in 2 steps. And here, I to j means without stopping at I somewhere along the way, right? So, or sorry, without stopping at j. So this is the first arrival at j after you were in I, right? And then and so on, you keep adding these up. I to j in 3 steps, right? And this just goes on forever. And so what this really is this is the probability that there exists some n greater than or equal to 1, such that I to j, such that you went from I to j in n steps. or ooh, it's long. In n steps. Like that. Okay. So I don't have a name for this guy. If I find one that was hiding in my notes, I'll let you know. But so if it's related to the first passage probability, but if you sum over all of those, it's saying that there is some n it's the probability that there is some n that will get you from I to j. Okay. All right, now we're going to introduce another kind of a state. This guy is the following. We say that if a state I is such that Fii is equal to 1, then I is called a recurring state. Should probably write better for a definition. So this is called a recurring state. Now think about what this means. So if you go back over here and say, what is Fii, right? So that's the first return probability. It's the probability of going from state I back to state I after n steps, right? Now if that's 1, what does that mean? If you think about it for a second. It means that you will definitely return to state I eventually, right? There's no n in here, right? So it means we've summed over all of the n's. So it means, does there exist some n for getting from state I to state I, right? So this means the following. So it means you will return. May take a while, but you'll do it. Or the system will do it or something. Okay, the next thing is similar. So definition for this guy, we'll say if Fii is less than 1, then I gets a different name. It's called a transient state. All right. And so think about what this means. So this means that if you sum up all of the probabilities of going from I to I in n step for all the different n's, and you get a number that's less than 1, it doesn't mean you're not coming back, right? From state I back to state I. But it means you might not, right? It means that you may not, even if you wait forever. So might not ever return to the state. So if you have a state that you may, it's possible, like you imagine some directed graph, like you could leave the thing and bounce all over the place, and it's possible to come back, but you don't have to come back, then we call that a transient state, right? If it's guaranteed that you'll eventually come back, we call that a recurring state. And it would help if I had written it correctly. Did I erase a letter or something? Jeez. Recurring state. What's wrong with me? Man. Okay. It's also called a persistent state. That recurring state. Persistent state. Okay. So a couple of comments about this. So note the following. Any absorbing state has to be a recurrent state. That's probably obvious if you look through it. Remember, an absorbing state is the state for which you get stuck in it, right? So it's definitely recurring. You're definitely coming back. In fact, you're coming back in the next time step. And the next comment of similar style is that ephemeral states are all transient. So these are sort of funny. I mean, they're obvious, I guess. But these are sort of funny types of transient states, right? Transient states, it says you might not ever return. You won't ever return to an ephemeral state. So that definitely is a version of might not ever, but it's a sort of the strong version. Okay, and just a couple of sort of another interesting point. Notice the following. If you have some recurrent state, right, so remember what that means. That means that the sum over n of Fii n is equal to 1. It means that you will return to the state. Then Fii n is the probability mass function. That is to say, it's the probability mass function for the event. So let's do this. We'll say for the event, or for, how do we say, for the not event, for the random number of steps before returning to state I. From state I. Right, so this is a probability mass function then. Since it's a probability mass function, we can do things like define an expected value. And so we're going to name the following thing. Right, so we're going to define the recurrence time. Right, so this is going to be the expected time until first return. Right, so that's to say mu I will be the name of it, so it goes along with each individual state. There's one for each individual state. And so this is a sum over all n of n times this PMF, Fii n, right? So that's what we call that the recurrence time, right? And we're going to introduce two different types of states based on what their recurrence times are. So one is going to be, so we'll just make two new definitions. So remember I said these just keep coming rapid fire here. So we say a recurrent state, recurrent state, which is, we'll say a recurrent state is I, is called positive recurrent. If the following is true: mu I is less than infinity, right? So that means that the recurrence time is finite, right? Then we say it's positive recurrent, right? And as another definition, same kind of thing, but we'll say if it is equal to infinity. So if it's an infinite thing, we have a different name for it. we say it's null recurrent. So these are sort of a lot of definitions. Some of them are really short, like null recurrent and positive recurrent, but other ones are a bit longer. We'll probably have to go back through and highlight just to make sure we've got a clear location of all the new words. But we're now going to introduce a sort of a longer definition. It's a little more interesting, I think. So this one is defines something called a periodic state. So we'll put that word at the very end of this definition. But let's first just kind of describe what this is. So suppose you have some set that I'll call Q. Sorry, that's pretty sloppy. Q. Call this set Q. And it's a set of a collection of integers, so all possible n's, such that the probability of going from state I back to itself in n steps. Now, this is a P, so it's not an F, so this means it goes from state I to state I and after going through n steps. It can also go through state I during that process. So it might, let's say I was state 1. You might start off at state 1 and then go to 2, 3, back to 1, and then 4, 5, and then back to 1. That whole stretch is an n that qualifies for this set. It's not the first return value. Okay, and so for this probability to be greater than 0. Right, so this is the set of all n's that it's possible to return to the state by. Okay, so we'll say this is for state I, obviously, since I is the index there for the P. So this is all times that it's possible to return pi. All times possible to return by. And then we'll say, so this is just a set of all the times that you can return back to where you started from. And we'll say that if there exists some quantity tau, so if there exists a tau greater than 1, such that, you can express the elements of Q as follow, or you can re-express Q as Q is equal to the set of all k times tau, such that k is 1, 2, and so on. So if that's possible, and if tau is the largest value that works for this, we'll go back through and sort of make sure we understand what this is after we rate it. So in other words, it's like the greatest common denominator, or greatest common divisor. Then we say that the state is periodic with period tau. Okay, so this is a bit of a long definition, so let's think about what it means. So Q is this set of all the times that it's possible to, all the numbers of steps that it's possible to take before you return back to the state that you started from. And this is all referring to one particular state, so we're trying to describe one state. If it's possible that all those numbers of steps are multiples of a particular value, and that sometimes there's more than one of those things, then the largest of those is called the period, and the state is called periodic. And we'll do some examples to try to make this clear. If there's not such a value, we say the state is aperiodic. So if there is no such tau, state is aperiodic. Oops. Okay. So in other words, if the state is periodic, then you can only return back to where you start, back to that state, after trips that take multiples of tau, or some smaller value. Okay, and we're going to do an example here in a second. But before I say that, I'm going to introduce one more term. A whole lot of definitions, man. If the state is positive recurrent, you should think about what that means. So if that's the case, and it's aperiodic, oh, well, what does that mean, right? So I'll just write it out. That means that you will return eventually. And you have a mu I that's finite, an expected recurrence time that's finite. So if the state is positive recurrent and it's aperiodic, so no period, then we call it ergodic. Okay, let's try an example and see about how this periodicity works. So let's imagine sort of two loops, right? There's a set of 4 states over here. Right? So there's a probability of a half for going either different direction here, away from state 1, right? Now let's suppose all the other states are linked like this, and each of these arrows has a probability of 1. I won't write all those different ones, right? So the idea here is you start, so let's say you start off here, or that's the state that we want to kind of classify. You don't have to start there necessarily, but let's suppose we want to classify this state. So we imagine being here, and what happens? Well, there's different things that can happen, right? So you could go this way, and then you will come back like this, right? And then once you get here again, you either can go to the right or you can continue going to the left, like this. And then the same choice occurs again, right? So that's one possible type of thing that can happen. Or you can do that same kind of thing on the other side, right? So you can come around like this, and then you can keep doing it again, or you could have gone back into the other loop, and so on. So those two types of paths are possible, and then there's paths like this that are possible, right? And then all different combinations of those sorts of paths, right? So let's first try to figure out, okay, is state 1 periodic, right? So let's try to make the set Q. So state 1 periodic, right? So we'll make Q for state 1. I'm going to write it off to the side, actually. Right. So what does this look like? The set of all possible integers that it's possible that will let you come around, right? So let's just sort of start to count them up. So clearly 4 works, right? There's 4 steps there. So 4 is possible. And you could repeat that over and over again, that same loop, right? So then 8 is possible, 12, and so on. So integer multiples of 4. So I'm going to write that over here, k times 4. Right, so that's one possibility. Another possibility is just going around loops on the right, and those come in multiples of 6. So you see 12 shows up again. So this is k times 6. Oops. And now let's sort of look at these mixture ones, right? So let's count some of those up. So suppose you did this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 gets you there. I think that's the smallest such thing you can do. And then let's start counting up others. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the same. 1, 2, 3. So you could keep doing this, right? So you go through a loop of 6, a loop of 4, and then you just have different combinations of that. So I think the next one you can get to is 14, and so on. So the pattern is then it's some integer times 4 plus another one times 6. I'll call it m. Right? So that's what the set Q looks like. So this is pretty sloppy notation here. Those things k times 4 and 6 and 4 and so on shouldn't be in the set description or definition here. But so that's what this thing looks like. I don't think there's any other routes that get you back to state 1, but it's always good to try to look. So are all those numbers multiples of any other number? Well, clearly they're all even, right? So 2 is one that works, but is there something else? So a next natural choice would be to look at is 4, but that doesn't work because 4 doesn't divide 6. So I think it's 2, right? So this guy 1 is periodic, so the answer is yes, and tau is equal to 2. Right? So that's how this works. Let's try another one. We'll label this guy over here state 2. Man, I got really small there. And we'll go through the same exercise where we count up different roots. All right, so we start here and go 1, 2, 3, 4, 5, 6. So multiples of 6 are definitely going to work. Right? So for this guy, so is 2 periodic. And so we've got Q2, and it certainly has elements that are multiples of 6. So K times 6. And then let's look at the other possible roots you can have. So you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 would work. Just put that down there. And then if you keep doing those, coming around like this, and then adding in loops like this. Did I start at 2 at that time? It should start down here. What you'll see is that you always end up with this same kind of situation here. So k times 4 plus m times 6. Right, so this is k times 4 plus m times 6. Again, this is pretty careless, the way to write this, but I find it useful. And so then the answer here is also yes. And again, the greatest common divisor of all these numbers is 2. So you might have thought 3 or so, or there's other ones you could try. 3 doesn't divide 10. So yes, and tau is equal to 2. Okay, so those are both examples of periodic states. All right, just a few more definitions. How many left? Two definitions left, and then we'll do one last example. Okay, so we're going to define if Pij for some n, so this is the n-step transition probability matrix, is non-zero for n greater than or equal to 0. Now 0 for the number of steps might seem odd, but we'll get to that in a second. Then if this is the case, which is common, we write it as we are denoted in the following way. We say that you can get from I to j. Right? So we write that symbol saying that it's possible to get from I to j. And we say, there's different ways to say this, but we're going to say j is accessible from I. Right? So that's just the definition of this word, accessible, and the notation I pointing to j. All right. You'll sometimes, I think some books will call this I communicates with j, but there's a good reason not to use that term because we're about to use it sort of, almost, again for something else. So here's the next one, the last definition of the day, I think. We'll say, if you have j is accessible from I, and I is accessible from j, then we say, we write the following. We write it like this. It's kind of obvious choice. And we say, I and j communicate. So that's why I didn't want to introduce that term for the previous definition. We're going to say I and j communicate means that you can get between the two in either direction. Sometimes people say intercommunicate. I think I've seen this before in books where the first one, they say I communicates with j. That's the first one, means this one over here. And the next one, this guy over here, they say I and j communicate. There's sort of no direction to the state. So for this they'll say I communicates with j, and for this they'll say I and j intercommunicate. But I feel like this is a really subtle difference, so I kind of try to avoid the word communicate for up here. So this means, this is what I'm going with. Accessible from I is this, and communicate means that you can go both directions. All right, let's try a fun little example. I think this is a cool one. We're just going to, this is kind of the typical sort of thing you might see. So let's write out an example where you just have the directed graph, and then we're going to do a whole bunch of different stuff with it. We'll try to wrap things up from what we've seen. We'll try to write the probability, the one-step transition matrix, and we'll try to classify some states. Okay, so let's say you have 1 over here. Okay, now, so this is sort of the problem, and I want to do the following things. Write down, the transition probability matrix, the one-step transition probability matrix, and classify some states. And I'll just put that sort of vaguely, and then I'll sort of tell you what I mean by that when we get there. So first, let's try to write down P. Now, how many states are there? There's 6, so this is going to be a 6 by 6 matrix. And again, I think we should start with rows. So we'll start in row 1 like this, and ask ourselves, If you start from 1, what's the probability of coming back to 1? Well, it's 1, right? And if you start from 1, what's the probability of going anywhere else? It's 0, right? 2, 3, 4, 5, 6. Okay, now we look at row 2. You start from state 2. What's the probability of going to state 1? 0. Going to state 2, also 0. So you can only go one place, and it's state 3. Like that. And then for state 3, you can actually go 2 places. You can go to state 1, and you can go to state 4. So you can get fast at these once you do a few of them. State 4, there's 2 places you can go. You can go to 2 or 5. And then state 5, you can only go to state 6, and from 6 you can only go to 5. Like that. Well, that was messy. Right, so that's P. Maybe I'll shrink it and move it off to the side. Oh, I don't know, it's fine like that. I'll move it over here. So that's P, we've done that. Let's try to do some classifying of states. All right, so first of all, which states are communicating pairs or intercommunicate? Which pairs, which states communicate? If you haven't noticed, I can't spell very well. It's common mistakes I make with spelling. It matches well with not being able to have clear writing. Okay, so remember, this means pairs of states that you can go from one to the other and the other direction. Or you can get from state I to J and from J to I. All right, so let's take a look. Well, this guy's a little bit funny. There's no one you can go to other than itself, right? So that's out. From state 2, you can get to 3. And from state 3, you can get to 2. So 2 and 3 are a communicating pair. Right? And you should work through all these. Any of these, anything in this little triangle here, any pair of states is a communicating pair. So that's 2 and 3, 2 and 4, and 3 and 4. Oops. Are there any other ones that you can see here? You should think about it. So not in that triangle, but you can certainly, these two, right? You can get from 5 to 6, and you get from 6 to 5. And so that's another pair. Okay, so those are all the communicating pairs. The next thing I want to ask is, let's see, which one should we do next? Let's say, which ones are recurrent? Right, now recurrent means will return eventually. So let's take a look at these. So if you start at 1, will you return to it? Yeah, that's the only thing you can do, actually. So 1 counts. And how about in state 2? Well, you could return, right? You could come like this, but you don't have to, right? So you could go from here and then to here, and then you're now stuck forever in state 1. So 2 is not a recurrent state. You don't have to return to 2 once you leave it. And the same story is true for 3 and 4. So these are not recurrent. This one is. And then both 5 and 6 are recurrent, right? If you're in those, you're going to be coming back to them over and over again. And so for these, the answer for this is 1, 5, and 6, right? Okay. What about transient? Right, so which one of these states are transient? In case you've forgotten what that means you might not return. And then from that story we just told, I think you can tell what these are. So it's definitely not either of these, and it's definitely not these. Those are out. But it is in fact these. So you could return from any one of those back to themselves, or you could get stuck either in states 1 or in that pair 5 and 6 on the right. So 2, 3, and 4 are the answer for this. Okay, and the last one, which is a bit harder, periodic. Which states are periodic? It turns out it's okay for this one. Sometimes it's quite challenging. But so let's see here. State 1, you might think, yes, it's periodic, right? You can go here, oops. You can go from state 1 to state 1. But if you look back at the definition, the number, the tau has to be bigger than 1, which I think you can sort of imagine has to be true. Otherwise, it doesn't make sense. Anything is periodic if tau could be 1. So 1 is not periodic. 2, 3, and 4. So let's think of the number of steps it's possible to return by. So if we start from 2, this route doesn't get you back to 2. The only way to get back is to come around like this. So there's 3, 6, 9, and so on. And the same is true for 3 and 4. So multiples of 3. So 2 has, 2, 3, and 4 have tau equals 3. And then if you go back up here and look at this pair here, these are also periodic. It takes 2 steps to get back to them. And so 5 and 6 have tau equals 2. And I think that's it for this particular example. I just realized I meant to tell you one last thing up here for communicate and intercommunicate. I forgot to include this bit over here, so let me put this last thing in on the side. We'll say that if Pij, we'll say Pij of 0 is equal to, well, how do I want to say this? It's either, hang on. We're gonna say Pii of 0 is equal to 1 for all I. I should have said that right when we were doing this, because I forgot it. Right, so therefore, all pairs of i's, or all pairs of i's, all states intercommunicate with themselves or communicate with themselves. That's a bit of a funny situation. I mean, this is true for all states. They all communicate with each other, with themselves. So when you get to something like this and it says list all communicating pairs of states, you don't need to list 1 and 1 or 2 and 2 and 3 and 3 and 4 and 4. So remember, this is transitioning from your state to back to yourself in 0 steps, meaning it's some kind of weird nonsensical situation where you're not actually taking any steps. And so we just define this to be 1. But we don't really list that when we're asking for the intercommunicating states. Okay, that's all I have to say for you for today.